Hi, I'm Nicole Hubbard, and I'm a developer advocate for HashiCorp. One of the things that we constantly see from our customers is the difficulties that they have when they are trying to secure the communication between their services running inside of a Kubernetes cluster, whether that be the communication just for the apps inside the cluster or communicating with apps outside of the cluster or communicating with apps between clusters. So to help solve this, we're going to talk a little about Consul Connect and using Envoy with that. And so this is going to be kind of a 101 level intro to Consul and all of the different features that Consul Connect provides. So one of the things that happen throughout the process of the DevOps transformation that we've seen is the migration from monoliths to microservices. And customers are constantly moving towards microservices and having more and more services as they go. And so this has led to the rise of the service mesh. And if you look at the different ways you can run applications, you can run them everywhere between mainframes to your own hardware in your own data centers, virtual machines, or even as far as containers and functions that are serverless. But the one thing that's common between all of these is the network. You have to secure the communication between all of the different services, no matter where you're running them. So if we look at an example of a traditional data center, you have your perimeter firewall that everything's encapsulated and blocks all the outside traffic from getting into. Then that traffic then flows in, hits your load balancer, and then that load balancer splits it between your 3 web instances in this case. You then also have an additional firewall that's trying to secure the communication between your web layer and your database layer. And this is in case someone gets into your network through your web application so that you can limit the access to the database and other things within your network. But as we continue to grow, we start to move into this new modern data center where you no longer have this hard perimeter around your network. You've got a VPN connecting you to another network. And so combined, you've got 2 external firewalls between those networks. And not only is it just your web application that's talking to your database, you're now replicating that database to another database in your other data center. You're also running potentially Kubernetes and running handfuls of services in those clusters that need to be able to talk back to that database. So as this continues to grow, you have more and more network security rules that you have to maintain. And you can do this through a bunch of different approaches. But as you continue to grow, some of the traditional ways of doing this start to not scale anymore. And so if we look at monoliths and microservices, we can take a look at a monolith here. It's made up of a bunch of different subsystems. In this case, we're using 4. And the nice thing is, whenever these subsystems need to talk, it just happens with an in-memory function call. So A can talk to B. Everything's shared in memory. There's no network calls. There's no figuring out how do I talk to this. It's just right there with an in-memory function call. But as you grow and you start to break these out into microservices, now you run into the problem of how does A talk to B? How do I find where B is? And so there's a bunch of different ways you can solve this. One is you can use a static IP address. But as you continue to grow and you need to scale out your service, so now all of a sudden we need 3 instances of B. How do you keep those IPs in sync? How do you handle when you do a new deployment and you get 3 new ones? Do you also have to deploy your old applications to update that? It won't work in the long run. So one of the things a lot of people do is they'll add a load balancer here. And this gives you a single point that you're able to talk to from your service A to get to service B. You talk through it, gives you a hard endpoint. You can scale service B up and down. But the downsides here is you've added a single point of failure. Now instead of only having 1 network hop, you have 2, one to get to the load balancer and then one from the load balancer back to the service. And you're increasing the complexity of the infrastructure you have to manage, as well as the cost of all of that infrastructure. So Consul provides some services that can help manage this. So as you have dynamic infrastructure that's constantly changing, you start to run into 3 problems. Service discovery, which is how do I find out where my services are and how do I talk to them? Service mesh, which lets you compartmentalize, which lets you break your network into components and control how they communicate with each other. and then service configuration, which allows you to create rules about what's allowed to talk to what. And so you can think about those as firewall rules in our old examples. So first, let's talk a little bit about service discovery and the service registry. So what happens now using a service registry is service B comes online. We've got 3 instances of it running, and those instances register themselves with the service registry. And so we can see now that the service registry knows that the B service makes up these 3 IP addresses. So now when service A wants to talk to service B, service A can go to the service registry and say, hey, give me the instances for service B so I can talk to it. And you can also put health checks here so that the service registry will only return instances that are online and healthy. And so now the service registry returns one of those instances, and service A is able to directly connect to service B. And the nice thing here is as the IPs change, the service registry is updated, and you're able to constantly connect no matter where the instances are, even if they're across data centers. And so you've got this process of just registering, discovering, and connecting, all leveraging the service registry, but your connections are directly made without going through anything. The next piece is the service mesh. And you can see that we're going to segment our services. And in the old example, the monolith, we have our segmentation with firewalls on both sides. We've got the load balancer, and then we've got a DMZ firewall that's limiting traffic that's coming from outside into our monolith. Everything within the monolith happens with an in-memory function call, so there's not a lot of limits we need there. And then you've got your firewall that's limiting your connections back to a database. And in this case, we're using a static IP for our database server so that we don't have to do any discovery of those. But as we start to break this out into microservices, we discover that these services have more communication between them than just A talking to B. So we've got A needing to talk to B, C talking to D, D to C, and so on, going all the different directions. But we have cases where they don't need to talk as well. And so as we continue to grow, it starts to look like this. You end up with hundreds, potentially thousands of services that have different requirements of what they need to be able to reach to. And some of these could be very important services that you want to keep secure and only allow one thing to talk to. So your standard approaches to network security, like VLANs and firewall rules, start to fall down as you reach a larger scale. We have some banks that we work with that have as many as 4,000 services. That won't scale with VLANs or firewall rules without an extremely high operational overhead. So specifically though with Consul service mesh, so with a service mesh, there's 2 components that you need to think about. There's the control plane and the data plane. The control plane for us is Consul, and what Consul is responsible for is defining the rules, defining and tracking what services are available, as well as provisioning that information to the data plane so that the data plane knows how to move traffic around. The data plane is basically a pluggable proxy that receives this information from the control plane and uses it to route data correctly to the correct place. Another component to the service mesh is the certificate authority. And this allows us to do some really nice things around security. We're able to generate certificates to ensure that all communication between services is entirely encrypted. We're using TLS, which is the exact same encryption we use on the open internet. And this allows us to then treat our internal network with zero trust when it comes to security, and allows us later to be able to do things over the internet without having to worry about the encryption or the trust between services. These certificates also provide identity so that the services talking to one another know for a fact that the service making the request is who they say they are because of the certificate. And then the last component is the service access graph. And this allows us to define how the services communicate. So if we look here, we have an example of creating a console intention through the command line. And the first one that we create here denies traffic from the web service to everything. And then we remember that, our web service kind of needs a database. It's important. And so we create an intention for the web service to talk to the database service. These intentions are applied no matter where the service is running. So if we can move the service between data centers, we can run it in multiple data centers. But the same intentions apply across the entire service mesh. They're also applied in order of specificity. So when we make the connection from the web service to the database service, we see that there's a very specific rule that allows that traffic. So it takes precedence over the generic rule that says no traffic from the web service to anything. You can also manage these through the web UI in Consul, and this allows you to actually see them, edit them, as well as create and delete, just like you could through the command line. And then now that we have all of this and we understand kind of the pieces and how they work, but how do I make them work with my application? Well, that's the nice part. You can use something referred to as a sidecar proxy. So this is a proxy that just runs right next to your application. And it makes it where you don't have to change anything in your application to get all of these benefits. You get the mutual TLS between services, you get the authorization and access controls, and no changes to your application are made. The only thing that happens is when you want to talk from the web service to the database service, instead of connecting to a remote IP or a remote DNS name, you're instead connecting to localhost, which gives you that proxy. And we can see an example of that here in a minute. But to enable this within Kubernetes, we provide a mutating webhook, which you can enable with just a simple annotation on your pods. So if you specify consul.hashicorp.com/connectinject, and you specify that to true, we will use our dynamic provisioning piece to automatically add in your container or in your pod a container that runs the proxy for you with no additional configuration. There are additional annotations you can specify that will help you configure additional pieces, but that will get you started with the proxy being available. So in our example of our web server with the database running in Kubernetes with the injection turned on, we can see we have our web service here with our proxy. And when we make the first request to the database, what happens is that proxy gets the request from the web service and goes and talks to the Consul client running on the node that it happens to be on. And that works with the Consul server to find out where the database server is and what the address is. And then then your web proxy opens a TLS handshake connection to the database proxy instance. Next, the database proxy will then talk to the Consul client and server to find out if this is authorized. So that intention that we created earlier that says the web service is allowed to talk to the database results in a yes, this is authorized. And at that point, the proxy establishes the TLS connection between the other proxy. Had that been denied, the connection would have just been terminated at that time. But now that the connection is established, all of the traffic just flows through that connection securely as if we were talking directly between the services. No changes there. But since we're sending all of that traffic through proxies now, this gives us the ability to add some layer 7 traffic management to our HTTP request. So if you think about layer 4 traffic, you've got a request that comes in that's for web.service.consul, and that gets forwarded to one of our 3 web service instances. But with layer 7, we can add some additional features, such as HTTP routing, traffic shaping, and custom resolution. And so an example for this would be, say we have an API service. So any requests that come in for web.service.consul/API, we don't want to send to our backend web service. We actually want to send those to our API service. And so we're able to create an HTTP routing rule that says, for that traffic that matches that path, send it to service API instead. Also, strip off the API part of the path so that it's just getting the request as is. We're also able to do traffic splitting, which allows us to control and partially roll out new versions. So in this case, we have version 2 specified for our subset, And when a request comes in, we can actually split it, say 80% to version 1 and 20% to version 2. And then we can also do custom resolution. And so in this case, we're defining what subset v2 looks like. We're saying find an instance of our service that has the metadata called version set to 2 and route this traffic there. Another component is the mesh gateways. So one of the tricks with running service meshes is that they're mostly built around running them within a single Kubernetes cluster. Talking to things outside of the cluster, or things outside of the cluster talking to things inside the cluster and using the service mesh can be pretty difficult, but it becomes even more difficult when you start talking about connecting your service mesh across different vendors or environments. So say you've got on-prem hardware and software and clusters running in the cloud, and you want to connect those, that's where the mesh gateways come in. Not to mention, they can help solve some problems with network overlap. So in this case, we can see now our API server and our web servers are running in a cluster that has a 10.8.1.1 IP range. And our database is running in another cluster that also happens to have that same 10.8.1.1 range. With normal networking, this becomes very difficult to solve. Overlapping IPs are not something that's trivial or easy to solve, especially when you're using all of the IP range like we are here. But if we leverage the mesh gateways, we can actually route the traffic through the proxy for the API into the mesh gateway, to the mesh gateway for our other cluster, and then to the database. And all of that happens without us having to even worry about what the IPs are, because we're saying we want to talk to this service, not this IP address. Now, as you can see with the locks above those steps, everything between the proxy and the mesh gateway and the mesh gateways between themselves is encrypted with those TLS certificates we generated earlier. This also allows us to route the traffic between the mesh gateways over the public internet if we're using different vendors and we don't have a good solution to be able to connect those privately. And so this allows us to only do layer 4 traffic, but we can apply the rules before it hits the mesh gateways. And then from there, the mesh gateways handle all of the NAT traffic for us, as well as being able to pass this information securely over the internet. So how do I integrate this with Kubernetes? So in good news, we have a Consul Helm chart that you can deploy. And when you deploy that, by default, it will give you a Consul server cluster as well as Consul clients. And this Consul server cluster that you get will run entirely inside of your Kubernetes cluster. Nodes outside of your Kubernetes cluster can also talk to these. They just require network connectivity back to those pods that are your Consul servers. We also deploy Consul clients to all of your nodes. This allows all of the existing tooling that works around Consul using the client to continue to work even inside of Kubernetes, and allows the proxies an endpoint to talk to get the data they need to be able to pass your traffic. We also have our mutating webhook with the auto injection that you can enable, as well as the mesh gateways that you can turn on if you need to be able to facilitate cluster-to-cluster traffic. So let's look at an example of this. So we have 3 different environments set up. They're already connected with mesh gateways. That's what the little locks on the corners represent that connect them. One of them is running at AWS. The other one is an Azure Kubernetes cluster. And the last one is a Google Kubernetes cluster. So what happens is we create some VMs for our front-end application, and then we create 2 VMs for our back-end application, all at AWS. When a request comes in, an HTTP GET /, we have rules that say this goes from the front end to the back-end VMs. And we're using Consul to discover where those are and to flow that traffic through with standard service discovery. But then we decide we want to provide an API to our customers. And so now when a request comes in that's /API, we want those to go to our API instances that are actually running in Azure now. And so we build those services, deploy them. Then we decide we need a v2 of our API because we messed up v1. So before that, here's an example of what that configuration looks like. So here's the service router with specifically defining match anything for /API and rewrite that to actually go to service API. So we're back. Then we decide we need v2 of our app. So we update our existing API instances so that they are tagged as v1. And then we go over to our Google cluster and we actually deploy v2 of our API instances. And now we want to be able to send traffic 80% to v1 and 20% to v2 to help Canary test and ensure that all of this is running properly. So what we do is we create a traffic splitting rule. So we build it here and we just do a standard split with a weight of 80% to the service subset v1 and a weight of 20% to the service subset v2. And this is applied to our API service. Then we define what those subsets actually represent. So we tell it for v1, what that means is look at the services, look at the version in the metadata, and find the ones that are v1. And for v2, it's the same thing, but we're looking for the flag v2. And this allows us to control that resolution. So now we have that traffic flowing. All of the requests are still coming into the AWS front end, and they're being routed over those service mesh gateways into both Azure and Google, depending on whether it's going to v1 or v2. And at the same time, we're still properly routing /request to the initial backend services. And so what happens when the next thing we want to do is add a front-end pod at Google? So we deploy it. And since all of the intentions that we've defined and all of the rules that we've defined for the traffic apply across our entire service mesh, the exact same rules will apply. So now that we've had the front end running in both AWS and Google, if we send a request that's an HTTP GET /API to the front end at Google, that request will be split 80-20 between the version 1 and version 2 API servers, and will be routed over the mesh gateway into Azure if it needs to talk to v1, or will connect directly through the proxies to talk to the v2 API instances. And when the request comes in for the for the HTTP GET /, that request will be routed back to the backend VMs all the way over at AWS. And all of these mesh gateways are communicating over the public internet with no network connections between them. And they can even have overlapping IP ranges because the mesh gateways take care of handling all of those components for us. So as we've seen, this makes it extremely simple to deploy your applications across numerous clusters, as well as link them and control the traffic and how those can communicate with each other. Thanks.